Hello everyone, welcome back. So let us continue our discussion. We are in the 10th week and this is our first lecture. In this week we are going to study torsion. Now all of you have seen in different mechanical devices we have a shaft, as you can see on your screen, and these shafts often rotates, but for the time being let us consider this shaft which is static, and then just imagine if we have a bracket here which is connected at the free end of this shaft, the other end is obviously fixed, and then if we apply force at the end of the bracket, so P is the amount of force that we apply, and say this is the distance from the center of the shaft to the point of application of the force. Obviously this force will cause a moment at the free end, and it is actually acting along the longitudinal direction. So effectively it will create a rotational deformation with respect to the fixed end, as you can see, and because of that this circular shaft will be turned about its longitudinal axis, and this is what is called torsion. Now if you look at the symbolic representation of the torsion, we use it with two arrowheads, right? Okay, so this is the amount of torque that we apply, and in this case its value is P times L. Similarly, just imagine instead of a force, if we have say bracket here, and then we apply two forces of magnitude P, and they are separated by a distance D. Now because they are equal in magnitude and opposite in direction, obviously they will also develop a couple at the end, and that couple acts along the longitudinal axis, as you can see. This will also cause a rotation of the shaft, and because this is an elastic body and the fixed end has no rotation because rotation is 0 at this end, with respect to that end this circular cross section will actually rotate in this direction. So for that, if we just consider a better representation, as you can see here we have this circular cross section, and let us consider a small element of dx at a distance x. Obviously this is the longitudinal axis along which we apply the torque, say T. And then if we consider a line say marked as AB, or say PQ, then this Q point comes to Q prime. And the angle here, this angle, say it is phi. So phi is the angle of twist. Now the small segment dx, let us draw it here, as you can see, and let us mark the ends. So we have say AB, here it is AB, and then C D. So the B point comes to B prime, similarly D point comes to D prime, and the angle of rotation here you can see this is phi. Now from this diagram what we can see, shear stresses are developed And if we mark the shear stresses using a different color, so at this end we have shear stress acting this way. Therefore, on the other face, again, it will develop shear, and we'll also have complementary shears. That's how the shear stresses are developed at the surface because of the rotation phi. Now this angle or this angular deformation is actually the shear strain, right? So we can define shear strain. From the diagram we get B prime divided by the length AB. Now let this circular shaft is having a radius of r. Therefore, we can quantify B prime. This is nothing but r times d of, this is actually at the end, at the extreme end, over a length of L, we have total rotation phi. Obviously here we'll have d phi, right? And the original length AB before deformation is dx. So using these two, we can quantify gamma, which is nothing but r times d phi dx. So look at this quantity. It is actually the rotation over the unit length. So if the rotation is phi, then total twist over a length capital L, then this is equal to phi divided by L. Obviously, we are talking about small deformation, and let this be theta. So let d phi dx is equal to theta. That is angle of twist per unit length. Then what we get, shear strain is equal to r times theta. So we get the first expression of the shear strain, and as you can see, for a constant r, if we increase theta, obviously shear strain will increase. That means if we increase the angle of twist per unit length, we will produce more strain. Now, because theta is equal to phi by L, so you can also write gamma is equal to r times phi by L. Okay, so this is equal to r times phi divided by L. Now from Hooke's law, we know shear stress is equal to G times gamma, right? G is the shear modulus. Now in place of gamma, we can write G times r theta. So effectively we get the shear force distribution over a circular cross section, and you can see as we move away from the center, so if this is the center and the radius is say r, so if r equal to 0, then tau equal to 0, and as we move away from the center, we have more and more shear stress, which is maximum at the extreme end, that means at the extreme fiber. So first information, we get the shear stress distribution over this cross section, and if we draw that at r equal to 0, we have 0 shear stress, and at the full radius we have maximum value of the shear stress, and in between we have linear variation. So this is the distribution of shear stress over the cross section. Recall, in case of bending we had a linear variation. In case of torsion also we have linear variation, and if you look at the expression, we have tau by r is equal to g theta, right? So we get the second expression, and it gives us a linear variation of shear stress in case of torsion of a circular shaft. Okay, now we can also quantify the amount of torque that we apply at the end in terms of shear stress that we have just evaluated. For that, what we do? We consider the small strip you can see here, and let the area of this small annular ring is dA, and then over this incremental area we can find out the amount of force, and from that we can actually find out the torque developed by that small force. So let this be r prime, and at r prime we consider this small ring shown by this dotted line, which is having an area of dA. Now the force developed over that ring is tau times dA, that is the force, and multiplied by r prime is basically the torque that is developed because of this stress over this dotted portion of the circular shaft. And if we integrate this from 0, that means from center to the extreme fiber which is at r, then what we get? We get capital T, that is the total torque that we apply. Now if we put the expression of tau here, we get 0 to r. In place of tau we have g r prime theta dA times again r prime, so that is square here. Now we can further modify this expression. Let us take g theta common, because this is constant, we can take it out of the integral. So we have 0 to r prime square dA. Now this quantity you can identify, this is nothing but the polar moment of inertia, or IP, right? Okay, so effectively what we get? We get T is equal to g theta times IP. IP is the polar moment of area. And for circular cross section, we know the expression of IP, and that is pi r to the power 4 divided by 2. So what we have here, g theta, in place of IP we can write pi r to the power 4 by 2. So we have theta, which is equal to T by g times IP, and for circular cross section it is 2 times T divided by g times pi r to the power 4. Recall, theta is equal to pi by L, which is equal to T by g IP. So this is another expression which correlates the rotation of the shaft, that is phi, with the applied torque, right? Now from this expression we get two important properties of circular shaft, that is, if phi is equal to 1, then we have capital T is equal to G times IP divided by L. And this is called torsional stiffness. Recall the definition of stiffness. It is the amount of force required for unit deformation, and in case of torsion, it is actually the amount of torque required, here you can see, for unit rotation, right, over the complete length. Now, this expression is extremely important because we can use this expression to find out the value of capital G. If you take a circular shaft of length say L, and then if you apply a torque T at the end, so that is T, then what we can do, we can measure the angle of rotation, right? So if this way it turns, we can measure phi. The moment we measure phi for the circular cross section, we already know radius r, so we can calculate IP, and then we get G is equal to T times L divided by phi times IP. Just like during stress analysis, I discussed how to measure the Young's modulus of a circular specimen. Here we can measure the shear modulus using this expression. Now, again, let us consider this a special case. If we apply T is equal to 1, then we have phi is equal to L by G times IP. And this is called torsional flexibility. What is the definition of flexibility? If you recall, it is the amount of deformation for unit force. So we are dealing with torsional problem. So we apply unit force here, and the amount of deformation we have in terms of phi is the torsional flexibility, which is the reverse of torsional stiffness. Just like in case of bending, we define bending stiffness and flexibility. Here also, in case of torsion, we can define the flexibility and stiffness. Now, if I consider this circular shaft again and just consider a small area, obviously we can draw the stresses acting over this. So this is sigma 1 and sigma 2, and this angle also you can identify, this is 45 degree, right? Okay. Now, what is the relation between capital T, that is torque, and the shear stress developed? Recall, in case of bending also, we identified the relation between applied bending moment and bending stress. So let us just quickly identify the relation between torque and the shear stress developed. So now we have derived theta is equal to T by G times IP, right? So what we get is theta times G is equal to T by IP. Therefore, tau is equal to, if you recall the first expression we derived, G times R theta. So in place of G theta, if we write the expression, we have R times T by IP. So that is the relation between stress tau and the torque applied, which is T. We can further simplify this expression and we get tau by R is equal to T by IP, where IP is the polar moment of inertia. Now, if you recall the bending problem, we derived sigma by Y is equal to M by I. A similar expression we have derived in case of circular cross section under the action of a torque of magnitude capital T. And here also we have a linear variation just like bending stress. As we move away from the center, the value of shear stress is more and it varies linearly from the center. Right. Now just imagine if we have not a solid circular cross section but a hollow, and say inner radius is R1 and outer radius say R2. Then what happens? IP is equal to pi by 32 times say D2, the outer diameter, to the power 4, that is the total IP if the section is solid, minus, because we have nothing inside, up to the radius of R1, so corresponding say diameter D1, so that is the expression of IP. In place of diameter, if we use radius, we have pi by 2 R2 to the power 4 minus R1 to the power 4. So then tau, we have T times say extreme fiber R2 is equal to, tau is equal to T times R2 divided by pi by 2 R2 to the power 4 minus R1 to the power 4. So effectively we have pi times T times, 2 times T times R2 divided by pi times R2 to the power 4 minus R1. So that is the maximum tau developed at the extreme fiber. So this is the maximum value of tau, or say this way. So it starts from the inner face, and at this face we have a value of tau inner face is 2 times T times R1 divided by pi R2 to the power 4 minus R1. Right. So this is tau in and this is tau max. And in between, again, there is a linear variation. So that completes the exercise. If we have a circular cross section, then if we apply a torque T, then we can easily quantify the stress over the cross section. We can plot the stress and we can also develop the relation for the hollow cross section, as you can see on your screen. So in our next lecture, what we will do, we'll extend this formulation for non-uniform torsion, because in our case today we have considered uniform cross section throughout the length of the shaft. Now in reality we have shafts of non-uniform cross section mostly, and for that we'll see how we can extend this theory and find out the relation between the torque applied and the stress developed. So with that, let us close here. We will continue in the next class. Thank you.